In this session, we're going to talk about the basics of recycles. We're going to start with the questions, what is a recycle loop? Why did one of my streams on the flow sheet just turn red? We'll talk about some of the best practices that you can use when specifying recycle loops, as well as some of the common problems that we run into. We'll take a look at trace chemicals in recycle loops, situations where we might need to adjust the convergence tolerance. And then we'll have a moment or two talking about heat integration loops, which is a special type of recycle. We're going to continue using the simulation from the distillation webinar. This simulation is already specified with chemicals. I'm going to zoom out and move to find some empty space. Yeah, we're going to be working with very simple recycle loop problems. That makes it easier for us to see what's happening, what might be going wrong. You probably won't have a process this simple. It's just easier to see the principles on a very academic problem. I'm going to start by drawing a recirculation of flow. I'm going to have a stream of water and ethanol, which is being separated by a divider, and then use a mixer to mix it again. So I start with a feed arrow and a product arrow. I'm going to pin the palette, makes it easier to draw. I'm going to find the divider unit, and I'm also going to find the mixer. And just so we have something happening on the flow sheet, we'll add a heat exchanger. Yeah, this is going to be a very simple process. You wouldn't normally have something this simple. Now when it comes time to connect streams, I'm going to start at the feed, connect to the mixer, the heat exchanger, the divider, and then I'm going to recirculate a flow, clicking to put waypoints down. Now I do apologize. Some people are very good artists with CHEMCAD. As long as I've used this program, you would expect I could draw pretty pictures. I can't. So I'm going to try to quickly move this. And a trick I use, if you don't have the time to make your picture pretty, just move things on top of it. I have crooked lines here. I don't feel like trying to make them straight. I'll just put the ID numbers on top. Now we've drawn a recycle loop. We waited for a moment, and one of the streams just turned red. If I pressed save, it would have turned red. Why did CHEMCAD make that turn red? Let's think of what we've just done. We've made a closed loop on our flow sheet. I've changed to a presentation which has a different stream marked red. We'll talk about how to do that later. This is a similar flow sheet to what we've just drawn. Why did CHEMCAD make this a red stream? This is a place where we have a circular reference. When we start calculating, the red stream is where we have a value of x, our initial value of x. We calculate around the flow sheet, and we have a new value of x, which is based on our previous value. Thinking back to numerical methods classes, we might start to think of terms like Euler method, Wegsting, direct substitution. These are ways to solve this iterative calculation. x1, calculate. Does x2 equal x1? If it does, we're converged. If it doesn't, let's perform another iteration. The red stream is showing us where CHEMCAD is declaring I am performing iterative calculations. Internally, CHEMCAD is really doing this when it starts calculations. It's considering that red stream to be a cut. Here, recycle streams talked about in process simulators as cut streams, tear streams, because this is where we're cutting the stream to perform iterative calculation. So that's what a recycle stream is, and that's why ChemCAD just changed it to be red. Going back to ChemCAD, ChemCAD specified this as the cut stream. There's an algorithm in ChemCAD which tries to determine cut streams. To be honest, it's trying to avoid bad cut stream points. If you're very interested in these mathematics, it's still possible to get your PhD with a dissertation, how to best pick a cut stream. If we want to choose a different stream, we can go to Specification menu, select Cut Streams. That allows us to specify a different stream to be the cut. I'll do that now to make my picture consistent with this presentation we just looked at. Later on, we'll talk about why you might choose a different cut stream. Let's start by specifying the flow sheet. I'm going to go into the feed. I'm going to change the comp units to kilogram per hour. I'm going to use 900 kilograms per hour of the isopropanol and 100 kilograms per hour of water. I'll specify temperature of 25 degrees and 1 bar. And out of habit, I always press flash. I want to see the calculated vapor fraction so I can think about it and make sure that the thermodynamic model is not doing something unexpected. Press OK. Specifying this flow sheet, the mixer doesn't need to do anything. The mixer will take the recirculated flow and mix it with our feed. If we go into the heat exchanger, to be honest, I put the heat exchanger here so we would have more units on our process. I don't want to do anything complicated with this flow sheet, so I'm just going to specify temperature out of 25 degrees. I press OK, and then I come to the divider. And this is where we often get into trouble with the recycle loop. I'll show you the way that I do not want you to run recycle loops. I'll start with how I don't want you to do things, and then we'll talk about the better way to do things. I'm going to change this to mass flow rate split. If I specify one of the outlets, ChemCAD will back calculate the other. Now, typically, when we look at a problem like this, we think, I'm going to specify what comes out of the process, because we normally know what we want coming out. If we're modeling an existing process, we might know what is coming out. If we're designing, we know the capacity that we want to produce. So let's do that. And I'm going to move the dialog here to cover my upstream flow sheet. Let's pretend that I have an extremely complicated flow sheet. Let's pretend I have dozens of unit operations, and I know that I have a production requirement of 500 kilograms per hour at least. So I might specify stream 19, which is leaving the recycle loop, 500 kilograms. When I press OK, when I press run, we're going to perform iterations around the loop. The default number of iterations in ChemCAD is 40. We can change that if we'd like. But when I press Run All, ChemCAD will start at this stream. It will cut stream 20 and say 0 flow rate plus the flow coming in. It will come through reach the divider, and it will say the recirculation is the flow rate which arrived at the divider minus 500 kilograms per hour. So we press Run All, and we see that it's running, and we have a new message. Recycle calculation did not converge. This is a simple flow sheet, so we know what happened. It's very obvious on a simple flow sheet. We specified 1,000 kilograms per hour entering, and we specified 500 kilograms per hour leaving. That won't work. We see the type of message that you receive. We have a message, recycle did not converge. And we'll see that in the errors and warnings tab. Our unit operations all converged, so there are no red lights on the flow sheet. Because the recycle calculation did not converge, this is not our converged flow sheet. If I were going to build a process, I would not start from this current specification. The recycle didn't converge. This hasn't found the answer. So that's a bad way to specify a recycle. Now I'll show you the way that I would specify this. If we go back into the divider, I'm going to delete that outlet flow. There are two reasons this is a bad way to specify. Reason number one, you can specify something that doesn't match mass balance criteria. The second reason it's bad to specify what leaves a recycle loop, that means what stays in the recycle loop is X. There might be an infinite number of answers for X. There might be 5 answers for X. That's multiple solutions. That's hard to find. Whatever your starting value is will determine your final value. So the better way to specify a recycle loop is start by specifying what stays inside the loop. Let the mass balance determine what comes out. So I'm going to specify what stays in the loop. I'll specify that I want 200 kilograms per hour to stay in the loop. I press OK. Now when I run the flow sheet, recycle has converged. So we can use these values. This is an answer to the problem that we specified on the flow sheet. If we look at the flows coming out, yeah, we have 1,000 kilograms an hour coming out. So that's calculated by mass balance. Yeah, this is a very simple example. So we expected 1,000 coming out. Now if I zoom out, I'll show you how I might actually start this if I'm drawing the simulation. Yeah, this simulation, we closed the recycle loop when we started the drawing. But this is how I would draw a recycle at first. I would start with my feed. I'm going to add an extra feed at the top. I'm going to have the product stream. I'll add an extra product at the top. I'll have my mixer, my heat exchanger, and a divider. And as you might guess, what I'm planning to do is I'm planning to break the recycle on my flow sheet. Now, I just used a command on a stream. I made a mistake with the drawing. I performed right-click on a stream and reroute to redraw the stream. Just in case someone saw that and wondered how I did that. Okay, this is how I would start a recycle flow sheet. I would initially have a separate feed and a separate product. I would specify it the same way I intend to run. I would specify my feed is 900 and 100 kilograms per hour. Because I've broken the recycle loop, I need to make an initial guess for what's going to be in the loop. let's say my initial guess is 20 degrees Celsius, 1 bar, and 200 kilograms per hour of isopropanol. I'm just going for an initial guess to try and get my flow sheet converging. I'm doing one manual iteration of the calculation loop. I need to specify the heat exchanger at 25 degrees out, the same temperature I used. And the divider, I'm going to specify it the smart way, mass flow going back towards the recycle. So I'll specify 200 kilograms per hour going back towards the recycle. Press OK. When I run the flow sheet, after it converges, I'm going to look at the two streams, the two cut streams, and I want to see how close they are. I tend to use edit stream very heavily to compare streams. So this was my initial guess. This was x1. And this is the calculated value after one iteration, x2. My initial guess was 200 kilograms per hour of isopropanol. The calculated value is 183. That looks good. We're somewhat close. After running like this, I might connect the recycle immediately. Why am I doing this extra step? Well, if I made a mistake, or if I've got a larger flow sheet, I'm going to put a picture on the I'm going to import a picture onto my flow sheet. If I had a much larger process here, if I have different products coming out of this question mark, different feeds coming in, when this simulation runs, x2 may have been at 600 kilograms an hour, 5,055, and 700 degrees. I only want to perform one iteration of the recycle loop to see that my streams are that much different. If I perform one iteration of the recycle loop and I see this big of a difference, it lets me know I need to start looking into all of the unit operations on my flow sheet, and I need to find out why I'm not getting what I expect. I can do this one at a time. I can just work backwards. I can find out why is so much extra material coming to this branch. If I had specified a closed loop and pressed run, every unit operation in the branch would have unusual numbers. This would fail to converge. Stuart had a yellow light for a convergence problem earlier. I might have a red light on all of my units fail to converge. It's very hard to go through all of those units finding the problem. So that's what a recycle is, and that's a very simple look at the best way to specify a recycle starting out. And this does scale to more complicated flow sheets. And again, it's easier to specify what comes back into the loop. Another added benefit, you're stabilizing calculations. Instead of calculating what the flow rate is, you're specifying the flow rate. You only need to calculate the composition. That's one less variable. Quite often, if we're working with existing processes, or if we're looking at a design from someone else, we'll have a very large flow sheet. You might see a drawing, which is very complicated. You might be tempted to draw something like this in CHEMCAD before pressing run. I would not do that. I would draw one small branch like this, press run, and then add one recycle loop. Maybe add 2 or 3 recycle loops. If you've made a mistake in specification in the middle of this flow sheet, if someone gave you bad sensor data or a bad design flow rate for one value in the middle of the flow sheet, when you press run, this won't converge. It might take you hours to find where the trigger is. It might take you hours to find that this flow rate is impossible. If you build the flow sheet slowly, one step at a time, when you reach that branch, you'll immediately see something is wrong with my expectations and the calculated result. And you'll have the chance to decide what you might need to change. This is also a flow sheet that gives an example of why we might want to change the cut stream. I might have very good sensor data for this stream here. I might have a very good initial estimate for the flow rate and the temperature. I might be able to make a good guess from my judgment for the composition. This would be a very good cut stream because I can give a good initial value. With iterative calculations, the closer our initial value, the fewer iterations we need. That would be a situation where I might change and ask CHEMCAD, make this a cut stream, because I have a very good value. All right, the next thing we're going to talk about is we're going to look at what happens if we have a small amount of a trace component. We're going to add 1 pound an hour of nitrogen to a recirculating flow. So we start by adding nitrogen to our chemical list. I'm going to go to Thermophysical Select Components, and I'm going to add nitrogen. And I'm going to modify this flow sheet. I'm just going to select and move this section. And I'm going to insert a unit on this area. Yeah, we're going to perform a flash separation. We're going to make this more complicated. So I'm going to insert a unit on the stream coming out of the heat exchanger. I can do that by right-clicking the stream and selecting Insert Unit. Yeah, I go to the Separators subpalette. There are fewer unit operations here. It's a useful subpalette, and I find flash number 1. I put that on the flow sheet. And then I'm going to add another product arrow and connect the stream. So we've just changed the problem that we're dealing with. I'm going to have vaporization of the feed. We're going to be recirculating some of our vapor, and we're going to be blowing down the liquid. I'm going to unpin the palette so we can see the flow sheet more clearly. Now you'll see me collapse the palette when I'm not using it. When you watch a webinar that I'm doing, if you see me use CHEMCAD in person, I never collapse the run trace or the errors and warnings. I always want to see the information here. We're going to change the way our heat exchanger is specified. Instead of specifying a temperature out, we're going to specify a vapor fraction. We're going to specify that we want to vaporize 20% of the material that comes in. We're also going to go to our feed, and we're going to add a small amount of nitrogen to our feed. Now, I could try to make a saturated flow of nitrogen. I could use CHEMCAD to determine how much nitrogen will dissolve in this stream. That's a more complicated topic. We do have examples of that on our support center. We might do that in a future webinar. For now, I'm just going to add 1 kilogram per hour of nitrogen and press flash. We see that we do have a small bubble of nitrogen. In reality, this might be entrained bubbles. CHEMCAD always insists on calculating the vapor and liquid phase, so it will be shown as a vapor. I press OK. So to review, we have 1,000 kilograms of alcohol and water with a small amount of nitrogen coming in, 1 kilogram per hour. Let's remember that number. We're going to vaporize part of this mixture. Then we're going to separate. We're going to recirculate the vapor. And right now we're specified for 200 kilograms per hour recirculation on the vapor. Let's run the flow sheet. And I may need to specify less flow. No, I don't. Okay. Recycle has converged. Recycle flow sheets will take longer to calculate because they're performing the same unit operation calculations again and again. While you're running the flow sheet, you might notice in the left pane, you might notice the green arrows updating as every unit runs. You might notice in the bottom left, CHEMCAD is telling you the unit number that it's currently calculating. Let's inspect our results. Now, with the recycle loop, there are a few things that I'm always interested in looking at. I'm always interested in looking at heat duties of units. I'm going to glance at some heat duties to see if they're large. Why do I do that? I specified a condition coming out. If I have a very large flow, I could have a very large heat duty. I once saw a simulation that had an unexpectedly large recycle flow rate. A heat exchanger in the recycle loop was requiring more energy than the output of the sun. The way the problem was specified, there were no errors because that's what we were asking the model for. So I might glance at heat exchanger heat duties quickly just to make sure that common sense and engineering judgment, I like the results. What I'm most interested in is the composition of the recycle stream, the composition of the inlets and the outlets. So I'm going to use specification menu, select streams. I'm going to click the first inlet, the recycle, and then the two outlets. And I'd like to see these in the same units. So I'm going to change them all to kilogram per hour. And you might notice something interesting. I'll point it out. Look at the nitrogen flow rate. Yeah, at the inlet, and I'll label these streams so they're easier. At the inlet, we have 1 kilogram per hour entering. At the vapor outlet, we have almost 1 kilogram per hour leaving. At the liquid outlet, we have a very small amount of nitrogen leaving. The nitrogen in the vapor and the liquid outlet, just from a quick glance, I don't think this adds to 1 kilogram per hour. Looking at the recycle, we've built up we have 6 kilograms per hour in the recycle. But what I'm really concerned about is just eyeball glance at the outlets. That doesn't add to 1. What's happened here? Did ChemCAD suddenly become very bad at math? Hopefully not. That would be a very bad thing for me. What's happened here is we're looking at a numerical tolerance issue. Now, I said that ChemCAD performs iterative calculations until the new value of x is equal to the old value of x. That is to a certain numerical tolerance. 2 plus 2 equals 4 for large values of 2. 2 plus 2 equals 5 for large values of 2 and small values of 3. We're at a situation where ChemCAD is saying close enough on the mass balance. X, the new value of x is close enough to the old value of x. If we have only isopropanol and water, that's fine. The isopropanol and water mass balance. But we have a very small amount of a different chemical, of the nitrogen. So I'd like ChemCAD to be more precise. I would like ChemCAD to perform 2.00 plus 2.00 equals 4.001. I'd like ChemCAD to give me an answer like that and accept it. I don't want ChemCAD to say 2 plus 2 equals 4.3. I don't want it to accept that as converged. So I need to tell ChemCAD, be more precise with the answer you're looking for on this simulation. I do that by going to the Run menu Convergence. At this dialog, we have several settings that are related to recycles. I'll talk about some of them now and some of them again in a moment. To tell ChemCAD to be more precise numerically, we want to look at the recycle tolerance for flow rate. You see that by default, ChemCAD has a flow rate tolerance of 0.001. So ChemCAD is saying that if it looks at a stream with 1,000 kilograms per hour, plus or minus 1 kilogram per hour is close enough. For my purposes, that's not true for this flow sheet. I would like ChemCAD to be more precise. So I'm going to tell it 1 more 0. I might even tell it 2 more zeros. Normally the flow rate tolerance is the only tolerance you'll need to adjust. We're doing a sequential modular flow sheet. We'll talk about what that means in a moment. For sequential modular flow sheet, the other values are going to be dependent on your flow rate. If we have a more precise flow rate, we will have a more precise enthalpy, therefore we will have a more precise temperature. So I'm going to press OK. I'm going to run all. I specified a tighter tolerance, which means ChemCAD took longer to calculate. That's telling me it did not converge. ChemCAD by default tries 40 iterations. So it gave up after 40 iterations. I can tell it to run it again and get 40 more. I could go to Run menu Convergence and I could specify more iterations. I could say, I want you to do 400. Now, obviously, you should be careful with number of iterations and tolerance. If you specify a very tight tolerance and a large number of iterations, you might be waiting a long time for ChemCAD to converge. I'm going to loosen that tolerance a little bit just to make it converge for the webinar. All right, so we've converged at a tighter tolerance. And let's inspect the results. Let's look at the inlet stream, the recycle, our outlet. Now, I'm not sure if this was mentioned in a previous webinar, but when you put a name in a stream, CHEMCAD will put the text label for that name on the flow sheet. If we look at the outlets, by visual inspection, 99983,00017. This is a much closer value. This is adding up. I'm not using a calculator, just by eyeball. This is saying 1 kilogram coming in of nitrogen, 1.00001 coming out. So tightening the tolerance has made CHEMCAD much more sensitive to what happens with the nitrogen. Going back to run convergence, for this simulation we needed to use a smaller number for the tolerance. We call that a tighter tolerance, tighter than the default. If you point at the number, we do show you the defaults as a reminder. Sometimes we're asked, why doesn't CHEMCAD use a very small number for tolerance to begin with? Well, there are two reasons. One, that for a different flow sheet, that might be a specification that you can't reach. Also, that will greatly increase the calculation time on some recycle flow sheets. We leave it to you as an engineer to decide when you need to increase or decrease your flow rate tolerance. Something else that we'll see happen here. Sometimes users will say, recycle did not converge, so they'll decrease the tolerance. Please don't do this. I'm demonstrating it so you see what happens. If I tell CHEMCAD use a flow rate of 0.1, I'll get a warning from CHEMCAD that I'm using a very small tolerance, smaller than default, and that it may decrease the precision. If I run this flow sheet right now, CHEMCAD, when it converges a recycle loop, the mass balance might be 1,000 kilograms per hour coming in, 900 kilograms per hour going out. CHEMCAD will be happy with that because I've asked for a very loose answer. I don't think any of us as engineers would be happy with that. So if you cannot converge a recycle loop, the solution generally is not to use a looser tolerance. Now there's another setting on the screen that I'd like to mention while we're here. 2 or 3. Cut stream method. This has normal recycle as the default. On a complicated flow sheet, you might want to have Smart Cut be the setting. With Smart Cut, CHEMCAD will change recycles. CHEMCAD will do a quick analysis of your flow sheet topology, and it will try to come up with a more aggressive pattern for making the cut streams that might help converge the flow sheet faster. On the right, we also have sequential modular versus simultaneous modular. On calculation sequence, the default is sequential modular. The default with sequential modular, we do what I've been talking about. We perform an iteration around a loop. Different options. All I'm going to say about AutoCalc is please don't use AutoCalc. This is a legacy setting from DOS versions of CHEMCAD. A very small number of users have very specific simulations using that. Please don't use that for a new simulation. Simultaneous modular. This is a different calculation sequence. In simultaneous modular, we make a matrix of unit operations. Each unit operation will be considered a row in a matrix, and we will perform simultaneous linear algebra calculations to try to determine what is the converged flow sheet. Simultaneous modular can be useful for converging a very complicated flow sheet. I've seen simultaneous modular solve a network with hundreds of unit operations on it in 2.5 minutes. That same network took more than 4 hours in sequential modular. We're not going to go too much into depth on simultaneous versus sequential modular right now. We are preparing some material for the support center on our website, it's not ready yet, keep an eye there. Keep an eye out for new material in our knowledge base on that. Also, feel free to ask us questions, email in when you might want to use sequential versus simultaneous. My advice, if you're having trouble with sequential, change to simultaneous, run it once, see if it converges for you. For more technical discussion, yeah, send us an email or give us a call. Okay, so I mentioned we were going to talk about a thermal recycle. Let me zoom out, and I'm going to add a thermal integration here, heat integrated loop. I'm going to insert a heat exchanger on the feed before the mixer. I'm going to insert a two-sided heat exchanger where we have utility flow and a process flow. I'm going to reroute my vapor leaving. Yeah, my vapor is leaving at 78 degrees. My feed is coming in at 25 degrees. I would like to reuse this vapor to preheat before I reach that heat exchanger. So I can draw a thermal recirculation. If I press save, that's going to force CHEMCAD to look for a recycle. If I run just one unit, that will force CHEMCAD to look for a recycle. So it's found a second recycle here. To make this easier to look at, I'm going to change the recycle streams. And to make this easier to look at, I'm going to choose, we have the material recycle, and we also have a thermal recycle. Now I can specify a temperature out at this heat exchanger. I can say preheat of 60 to 60 degrees. And now you might need to glance at the stream number on your flow sheet and compare it with the stream number in the dialog to make sure you're specifying the process stream out. Why press run all? This is a type of error that can happen with a thermal recycle, a pinch. Yeah, I specified that I want the process to go from 25 to 60 degrees. I have a pinch error because I do not have enough heat to raise the temperature from that high from my utility. If you're doing a thermal recycle, my recommendation is do something like what I demonstrated for the material recycle. I don't start my thermal recycles connected like this because it's easy to have a pinch error. On a large flow sheet, that might cascade downstream. You know, if I look at my utility stream coming out, it's very cold. CHEMCAD took as much energy as it could from that stream. On a larger flow sheet, it's quite likely that any unit operation downstream of this minus 270 will have an error or a warning. So that would make it hard for me to troubleshoot what went wrong. How did I specify this in a difficult way? So again, if I'm doing a thermal recycle, I'll start the flow sheet like this. I'll have two separate heat exchangers that I put close to each other. Yeah, I'll have my stream coming back to recirculate into a heat exchanger, and I'll put it close, and I'll have a new feed, which is my guess for what's in the recycle, and I'll have a new product. And if I do something like this, this is also a good time to use a note on the flow sheet. if I'm working on this simulation, I know that this is a drawing where I have two heat exchangers because I'm trying to converge my thermal recycle. I know that in reality, this is really one heat exchanger. If this is an important project and I'm sick tomorrow, or I get sent to a different important project, I think we all know that feeling, priorities changing, and I have to go out of country for a month, someone else might be told, here's a simulation, finish what David was working on. They might not know what I know, that this is two heat exchangers for calculation purposes while I try and find the answer. So while I'm doing this, I might put a box around them and I might put a note on the flow sheet. One heat exchanger, trying to converge recycle. I might even put do not build two. Yeah, I've been working technical support for CHEMCAD for many years. I see your simulations when they come to me and I send them back to you. So I've learned what happens when two people work on one simulation. We don't understand things that the other person knows are obvious. So I love putting important notes on flow sheets in case someone else sees them. Do not build is a note that I very much like to use. I might be using a heat exchanger for some simple mathematical purpose. I don't want someone to build that. So this is how I would start my flow sheet. How do I get the initial value for that stream, which represents my gas flow? Well, I can copy it from this stream. Now, there's a number of ways I can copy from a stream. I could do specification, copy stream, and say copy from stream 32 to stream 31. Press OK. Now when I run the simulation, it runs. I've still got a pinch error here. I only performed one iteration. If I've got a more complicated loop downstream, if I've got a more complicated process, to be honest, I would break that recycle as well, and I would draw a new stream here. I might put a note, don't buy a new feed, right? Just in case, I might put a note, these two will be connected later. If there's any calculation problem with this recycle, I've contained the problem. And then I can just make adjustments and say, okay, maybe I can raise the temperature to 25 degrees. Do I have enough heat to do that? Right, so I'm still, well, I don't think I actually ran the simulation. Okay, so 25, I'm still getting the warning that one of my flows is too small, so I just wasn't recirculating much. I can play games until I find something here that will give me a good answer, and then I'll connect the streams. Why am I so cautious with this? Because playing with CHEMCAD has taught me something. It's taught me that the second law of thermodynamics has no mercy. CHEMCAD has to follow the second law of thermodynamics. If we're doing back of the envelope calculations, we might not care that we're 1 or 2 million BTU off. We might not care that we're 1 BTU per hour off. CHEMCAD cares. If you're off by a little bit, you might not converge. So that's a quick look at some recycle loop basics. And to sum up, we've looked at what recycle loops are. We've talked about how they're calculated. We talked about some best practices for creating recycles. And this is how we do things in the office. The most important thing, don't start with a closed loop. If you make mistakes entering numbers into CHEMCAD, if there are mistakes with the numbers that were given to you, if the situation is just more complicated than anyone realizes, a closed loop could give you problems failing to converge. open loop, it's very easy to see those problems and then make adjustments or make theory exploration. Specify what comes back into the recycle loop. Typically, we'll do that with the divider. If you've got an open loop, this might help you see other problems, like it might show you don't have enough material coming back into the loop. So maybe you'll have to have a mixer and another feed stream. Maybe you'll need to do a makeup feed. You might see that you're removing a little bit more than what you expected from your downstream product. Maybe in reality, you're doing a purge every 24 hours. Well, in CHEMCAD, that would be a flow rate divided by 24 every hour. We've seen some of the problems that can arise with recycles. We saw what happens if you have a large flow of one chemical and a small flow of another chemical. Another situation where you might have that problem, if you're doing blowdown on a cooling water, you might have calcium carbonate or some other solid in a small flow. You'll want to use a tighter tolerance to do that. We've seen what happens when a recycle fails to converge. Now we've talked about the fact if a recycle has not converged, don't use the numbers. You're not at the real answer yet. The flow sheet itself might be okay. All of the unit operations may have converged. But you're several iterations away from the answer. There might not be a stable answer. You'll actually see this with old papers. One of our customers published a recycle network in the 1960s, recycle on a distillation column. He told me once they only did 2 manual calculations around the recycle loop. He was overjoyed with the first time he used CHEMCAD. He could finally see how close their answer was. They only did it 2 calculations because when you're doing that type of problem by hand, it took them 9 months to do 2 calculations around a column. We've also seen heat integration loops. We've talked about how do I recommend you approach a heat integration loop to avoid a second law of thermodynamic problem biting you and stopping the flow sheet from converging.